So here we have what's called the van der Pol system, or actually one example of a van der Pol system. You can put a parameter in the lectures, I call it epsilon in here, to really consider infinitely many systems that are all kind of similar to this. But this is one particular example. And our goal is to draw the phase portrait in the phase plane. The phase plane is the plane itself. The phase portrait, you're seeing what the solutions look like, just using null lines, nothing else. When we get to chapter 5 in the textbook, we'll use more tools to make sure we've got a pretty accurate phase portrait. For the x null line, that's where dx dt is 0. So that's equivalent in this case to y being 0. Since dx dt equals y, that's the x-axis, where y is 0. There you're going to have vertical tangents to solution curves. And the y null line is where dy dt equals 0. The original form written in the book is probably the easiest way to think about solving for the y null line. This expanded form we'll see is useful in chapter 5 when we do something called linearization. Solve that for y as a function of x to help you graph it. Add x to both sides, then divide both sides by 1 minus x squared. Y equals x over 1 minus x squared is a function, really, whose graph is the y null line in this case. It does have vertical asymptotes at 1 and -1, which you can see by factoring the bottom. So, you know, this graphing this is a calculus problem. Here's the phase plane. I'm about to draw the phase portrait. The x null line again is y equals 0. That's the x-axis. The x null line gets crossed with vertical tangents. The y null line is the graph of this thing. If you use calculus techniques or your technology to graph it, you get a rational function with vertical asymptotes at 1 and -1. So this is supposed to be vertical asymptotes here. It's got an x-intercept at 0. That's also the y-intercept. Ends up looking something about like this. It's the y null line. It's not a solution curve, right? It's just a tool to help you draw solution curves. They have to cross this horizontally because it's a y null line, where dy dt is 0. Where x and y null lines intersect, which is only the origin, are your equilibrium points. So there's only one equilibrium point at the origin. Make a big dot there if you didn't, if you are trying to redraw things. Yes, it's just one point, but it's such an important point that I always try to draw big dots at equilibrium points. No other spots do the x and y null lines intersect. You might say they almost intersect as x goes to infinity and x goes to minus infinity, but they never do touch. To draw the phase plane, then, you got to think about the signs of these derivatives in these different regions. How many different regions are there that the null lines separate the plane into? I'm going to count first when y is negative, then y is positive. Down here, 1, 2, 3, 4, 5, 6 regions that the null line separates the plane into. Dx dt is easy. It's just equal to y. So it's positive when y is positive and negative when y is negative. You're going to have rightward motion of solution curves when y is positive and leftward motion of solution curves when y is negative. That's fairly easy. dy dt is a bit trickier. It's more complicated. But still, dy dt will be positive when this expression is positive and negative when it's negative. What I would do to try to keep it as simple as possible is I'd pick certain points, like maybe a point here where x is 0 and y is positive. When x is 0 and y is positive, well, that's 0. This is 1 times a positive number. The result is positive. It's got to be upward motion in here. And in fact, in this entire wedge here, you're between these two pieces of the y null line. Dy dt has got to be positive. So that includes down here as well. try a point over here. Perhaps since we're crossing that part of the y null line here, dy dt will be negative in here, but test a point to make sure, like x is 1 and y is 0. If x is 1 and y is 0, maybe just think about it there, or here, it doesn't matter. You get 0 there, you get negative 1 there. Yeah, dy dt will be negative in this wedge here between these two pieces of the y null plane. Turns out if you test points down here, you'll get a positive dy dt, and a point up here, you'll get a negative dy dt. So overall, solutions up here go to the southeast, and here they go to the northeast, southeast, down here, northwest, southwest, northwest. All I'm doing so far is just tools to help me draw solutions. Let's draw some, pick various initial conditions, maybe start down here. I got to go to the northwest. So I head up here, I cross this y null line with a horizontal tangent before going to the southwest. There's symmetry, something similar, but symmetric will happen up here. If I start with an initial condition low enough here, it looks, well, okay, no, it's still going to cross there and go to the northeast now. Maybe it's going to cross this null. Yeah, it's probably going to cross that null line if I'm down low enough, at least. Before heading back down to the southeast, it's got to cross the x-axis with a vertical tangent. In this region, it's got to go to the southwest. So something about like this, maybe. Oh, maybe I should pick an initial condition close to the origin. If I start right there, I got to go to the northeast, cross this y null line horizontally, then cross the x null line vertically. Looks like it's an oscillation that's getting bigger. But there seems like there's got to be a limit on how big it can get. Because uniqueness says distinct solution curves can't touch each other. Remember that? Either in the reading or the lectures. Uniqueness, which we do have in this context because it's a nice vector field. It's a nice continuous differentiable vector field. Definitely is going to hold, and it's autonomous. That's important too, to say distinct solution curves can't touch each other. Now, again, it's hard to get this perfect, but what ends up happening for the van der Pol system is that every solution except the origin, except the equilibrium point at the origin, approaches a periodic solution. Somewhere right along in here somewhere, there's a solution that when you follow it, it comes back to where it starts. Where exactly is hard to say. I'm just guessing here. But it is true, it can be proved that the van der Pol system has a periodic solution that's attracting as well all other solution curves except for the equilibrium point at the origin approach it as t goes to infinity. They don't go off to infinity. This one sort of looks like it's going to go off to infinity up here, but it's actually going to go up here and cross this null line before coming back down, and it's squeezed into here, it turns out. Okay, that's not a super great drawing, especially of that periodic solution. I did not draw that very well, I should say. By the symmetry, it turns out to be an oval kind of shape centered at the origin, and I didn't really draw it that way. But the main point about the uniqueness theorem for autonomous systems like this is that distinct solution curves can't touch each other. Though they're all approaching this periodic solution, they're all getting squeezed together, infinitely close to each other. Kind of amazing, but true. The flow property works here as well. What would the flow property say in this context? If I have an initial condition vector, y naught, whose components are x naught, y naught, what's the flow in this case? Remember, I put superscripts here. It's really a family of functions. When I say the flow, it's really a family of functions. It's really infinitely many functions. One function for each value of t. I emphasized last Friday that for a linear system, thinking of y naught as the variable, this can be found, the formula can be found using the matrix exponential. That was the beautiful generalization. This is a nonlinear system. No matrix exponential is available. However, the solution by existence will exist. And this will equal it, no matter what t and y naught are. Is there a formula for this? Is there some formula you can write down? No. Well, except when y naught is the origin, then it's trivial. It's just always the origin. But if y naught's not the origin, if it's not the equilibrium point at the origin, there's no formula you can write down for this nonlinear system. But you can still prove this solution exists. And we're saying the flow at the time t map equals that. Abstract. Can it be approximated? Yeah, numerical methods help you approximate different values of this for different y naughts and different t's. Euler's method is the first attempt to do so, but to tell you the truth, Euler's method is not super accurate. Though in this example, it doesn't do too bad because of the nature of this thing. Because this is an attracting periodic solution. But in general, you want to use other methods that are better than Euler's method. I'm thinking of something called the Runge-Kutta method is the best method to use in general. You can also prove, it turns out this is defined for all values of t greater than or equal to 0. That's not true in general, and that comes up in your homework problem. Solutions in some systems can go off to infinity in finite time. It's analogous to a vertical asymptote for an ordinary function. But here we're talking about parametric curves. We're not talking about ordinary functions. In this case, it doesn't happen. Though it would happen if you let t go to minus infinity. Some of these would go off to infinity as t goes to minus infinity very rapidly. In fact, so rapidly that effectively it's like they have a vertical asymptote. But not as t goes to plus infinity. The flow properties can still be proved to work. When you compose two functions like this, it's like adding their exponents. That can still be proved and is still important. Flow property is one name for this. Actually, a better name is the group property of the flow. Why is that a better name? It's related to the study of something called group theory. It's abstract algebra. I don't want to get into details. It's kind of like an exponent property, isn't it? It's like you can add the exponents, but wait a minute, they're not really exponents. They're related to exponents with linear systems in the matrix exponential, but with nonlinear systems, they're not really exponents. I'm not multiplying things here. I'm composing them, plugging one function into another. This still ends up being important in ways we'll continue to talk about.